The word impossible carries unusual weight in modern astronomy. Sometimes it marks a genuine physical boundary. Sometimes it reveals that an assumption was mistaken for a law. New telescopes do not make the impossible routine. They show which limits belonged to nature and which belonged only to our models. James Webb did not look into the young cosmos and destroy the Big Bang. It did not prove that the universe is secretly twice as old as we thought. It did not show that physics has failed in one clean, dramatic collapse. That version of the story is too easy, too theatrical, and not careful enough. The deeper story is more uncomfortable. Webb has not broken the universe. It has broken a comfortable story about how slowly the universe was supposed to grow up. For decades, we imagined the first galaxies as small, clumsy, unfinished things. The universe after the cosmic dark ages was supposed to be a construction site. Gas had to fall into dark matter halos. The first stars had to ignite. Those stars had to live, die, pollute the gas with heavier elements, and let the next generation form. Galaxies had to merge from smaller fragments into larger structures. Massive black holes had to begin as seeds and feed their way upward. The whole process seemed to require patience, and the universe seemed to have no choice but to obey that patience. Then Webb opened its mirror to the infrared sky and began finding galaxies that looked brighter, more numerous, more chemically active, and sometimes more structured than many models had expected at such early times. Some were seen when the universe was only a few 100 million years old. Some carried signs of dust and oxygen, which means stars had already lived and died before the light began its journey. Some small red points turned out not to be simple galaxies at all, but possibly compact systems powered by black holes that appear far too important for their tiny hosts. Every answer reduced one kind of crisis and sharpened another. This is the controversy worth taking seriously. Not the claim that Webb has disproved cosmology. It has not. The real argument is whether the early universe was a slow builder or a brutally efficient one. Were the first galaxies truly too mature, too soon? Or did we misunderstand what their light was telling us? Did stars form faster because the early universe was denser and richer in gas? Did hidden black holes make young galaxies look heavier than they were? Did dark matter assemble the scaffolding earlier and more sharply than our simplified pictures allowed? Or are we seeing, in real time, the gap between a successful cosmological model and the messy physics of how ordinary matter becomes stars? The answer matters because galaxies are not decoration. They are the engines that turned a smooth, hot universe into a cosmos with stars, planets, carbon, oxygen, water, and eventually observers. If we are wrong about how the first galaxies formed, we are wrong about one of the first chapters in the story that made us possible. The mystery is not that the universe exists. The mystery is that it became organized so quickly. To understand why Webb unsettled astronomers, begin with the simplest fact about distance. Light needs time to travel. The sky is not a view of space alone. It is a layered archive of time. The moon is a little more than 1 light second away. The sun is about 8 light minutes away. Alpha Centauri is a little more than 4 light years away. No. And the galaxies Webb studies at cosmic dawn are so remote that their light began crossing the universe more than 13 billion years before it touched the telescope. That does not mean those galaxies are merely far away in the ordinary sense. It means we see them as they were. A galaxy observed at extreme redshift is not a present-day object sitting in the distance. It is a fossil image carried by photons that escaped when the universe was young. The galaxy itself, if it still exists as an identifiable structure, has evolved for billions of years since then. Its stars have changed. Its gas has been consumed or expelled. It may have merged with other systems many times, but the light Webb receives preserves a moment from the deep past. This is why Webb had to be an infrared telescope. The universe expands, and as space expands, it stretches the wavelength of light traveling through it. Light that left an early galaxy in ultraviolet or visible wavelengths arrives here, stretched into infrared. The farther back Webb looks, the more that ancient light has been red-shifted. Hubble could see some of this distant history, but Webb was built to specialize in the red and infrared glow of cosmic antiquity. Its gold-coated segmented mirror, its cold instruments, and its location far from Earth were not luxuries. They were the price of listening to light that had been stretched almost beyond recognition. The telescope sits near the second Sun-Earth Lagrange point, about 1.5 million kilometers from Earth, where it can keep the Sun, Earth, and Moon on one side and shield its instruments from heat. Its mirror spans 6.5 meters, larger than Hubble's, and it gathers infrared photons so faint that ordinary warmth from the telescope itself would drown them if the observatory were not kept cold. The engineering is astonishing, but the purpose is simple. Webb was built to see the universe before it looked familiar. Before the first stars, there was no familiar universe. In the beginning, after the earliest hot, dense phase, space was filled with plasma, a fog of free electrons and nuclei. Light could not travel freely because photons scattered again and again off charged particles. Only when the universe cooled enough for electrons to join nuclei and form neutral atoms could light travel across space. That release of ancient light is now seen as the cosmic microwave background. After that clearing, the universe entered the cosmic dark ages. There were atoms, especially hydrogen and helium. There was dark matter, which had already begun to shape gravitational wells. There were tiny density variations inherited from the earliest moments. But there were no stars yet, no galaxies filled with light, no heavy elements, no planets. Gravity worked in darkness. It pulled matter toward slightly denser regions, slowly amplifying the faint pattern written into the young universe. The first stars ended that darkness. They formed when gas collapsed deeply enough to heat, to the point where hydrogen fusion could ignite. These first stars were probably not like the Sun. Without heavy elements to help gas cool and fragment into smaller clumps, the earliest stars may have been more massive, hotter, and shorter-lived than many stars forming today. They would have poured ultraviolet radiation into the surrounding hydrogen and carved bubbles of ionized gas through the neutral fog. Over time, those bubbles expanded and merged until intergalactic space became largely ionized. This was the epoch of reionization, the universe's second great clearing. This story is established in broad outline, but the details are the problem. How quickly did the first stars appear? How massive were they? How efficiently did the first galaxies turn gas into stars? Which sources reionized the universe? Tiny galaxies, massive stars, growing black holes, or some combination? These are not decorative uncertainties. They decide how cosmic dawn actually happened. The comfortable version of the story said that the earliest galaxies would be small and faint. That expectation made sense. Structure in the standard cosmological picture grows hierarchically. Small dark matter halos collapse first. They merge into larger halos. Gas falls into those halos, cools, forms stars, and then is pushed back by radiation, stellar winds, and supernova explosions. Feedback slows everything down. It prevents gas from turning into stars all at once. Galaxies grow, but they grow through conflict between gravity pulling inward and energy pushing outward. That conflict is why massive galaxies in the first few 100 million years looked like trouble. If a young galaxy is truly very luminous because it already contains many young stars, then either it converted gas into stars with unusual efficiency, or it accumulated gas unusually quickly, or the underlying dark matter structure formed earlier than expected. If many such objects exist, the problem becomes stronger. A single strange object can be a rare accident. A population is a message. The first years of Webb observations were full of messages that sounded, at first, almost impossible. There were candidates at redshifts beyond 10, beyond 12, beyond 14. There were bright sources that appeared when the universe was only a small fraction of its present age. There were objects whose inferred stellar masses seemed too high for the time available. There were compact red sources that looked like galaxies stuffed with old stars, but also could be black holes wrapped in gas and dust. The headlines became dramatic because the numbers were dramatic. But the word candidate matters. Photometric redshift is not the same as spectroscopic confirmation. Photometry estimates distance by looking at how bright an object is through different filters and identifying the pattern caused when light is absorbed by hydrogen and stretched by expansion. It is powerful, but it can be fooled. Dust, emission lines, unusual stellar populations, and active black holes can all distort a galaxy's color. Spectroscopy is stronger because it spreads the light into its wavelengths and looks for specific features, such as breaks or emission lines, that can lock down the redshift more directly. This distinction is the first major counter-argument to the sensational story. Some early Webb candidates were revised. Some objects that looked impossibly massive turned out to be less extreme once astronomers accounted for active black holes, dust, or different assumptions about star formation. This does not make Webb less important. It makes the science better. The first pass through a new universe is never the final pass. It is a map sketched in dim light, corrected as the lantern grows brighter. One of the most important corrections concerns what became known as little red dots. These compact red objects appeared in Webb surveys of the early universe. At first, some looked like extremely massive young galaxies, potentially heavy enough to create a crisis for standard cosmology. But a more cautious interpretation emerged. Some of their light may come not from ordinary stars, but from rapidly feeding black holes. Gas falling toward a black hole heats and shines intensely. If that extra light is mistaken for starlight, the galaxy can appear to contain more stars, and therefore more mass, than it really does. This matters enormously. A galaxy's stellar mass is not measured by weighing it on a cosmic scale. It is inferred from light. Astronomers model the population of stars that could produce the observed brightness and colors. If a hidden black hole is contributing, or if the stellar population is unusual, the mass estimate changes. The lesson is not that the early universe was simple after all. The lesson is that young cosmic objects can disguise themselves. In this sense, Webb did not simply reveal early galaxies. It revealed the danger of assuming that ancient light behaves like nearby light. The local universe teaches us how stars and galaxies shine today. But the early universe had different gas density, different chemical composition, different radiation fields, and perhaps different typical star formation conditions. A color that means one thing nearby may mean something different near cosmic dawn. The controversy is partly a translation problem. We are reading a language written when the universe was younger, hotter, denser, and less chemically evolved. Still, the cautious view does not erase the puzzle. Even after the most dramatic mass estimates are softened, astronomers are still finding more early bright galaxies than many pre-Webb models expected. Some are not universe-breaking monsters, but they are still too common, too luminous, or too chemically active to ignore. The crisis becomes less like a collapsing building and more like a door that will not close. Something in the small-scale physics of early galaxy formation is more efficient, more rapid or less familiar than the old story suggested. JADES-GS-Z14-0 is a good example of why the mystery remains real. Spectroscopic observations placed this galaxy at a redshift of about 14.3, corresponding to less than 300 million years after the Big Bang. It is not described as a mature spiral stuffed with hundreds of billions of stars. That exaggeration would be wrong. But it is luminous, extended, and surprisingly large for such an early time. The light appears dominated by young stars rather than a growing supermassive black hole. Its existence asks a sharper question than the hype usually gives us. How did nature make a bright, sizable galaxy so soon? That question does not require us to abandon the Big Bang. It requires us to understand how gas behaved when the universe was young. Dense gas collapses faster than diffuse gas. A denser universe gives gravity more raw material and shorter characteristic times. If early galaxies were better at turning gas into stars, their brightness might be surprising without being impossible. In the modern universe, star formation is inefficient because feedback disrupts the process. Massive stars heat nearby gas. Supernovae drive winds. Radiation pressure pushes material outward. But in the early universe, deeper gas reservoirs and dense environments may have made it harder for feedback to shut star formation down quickly. This is where the claim becomes debatable. One side says Webb's galaxies do not threaten cosmology. They simply teach us that early star formation was more efficient than expected. The standard model of cosmic expansion and dark matter remains intact, while astrophysics inside galaxies gets updated. The other side says that if enough bright, massive early galaxies and black holes keep appearing, it may point to deeper changes in dark matter behavior, primordial fluctuations, black hole seeding, or the timing of cosmic evolution. The honest position is not to declare one side victorious. The honest position is to trace the mechanism and watch the evidence. The mechanism begins with dark matter. Dark matter does not emit light, absorb light, or reflect light. It is seen through gravity. It bends light from more distant objects. It holds galaxies together. It shapes the large-scale cosmic web. In the early universe, dark matter acted as the gravitational scaffolding into which ordinary gas fell. Without dark matter, normal matter would not have collapsed fast enough to form the observed web of galaxies by today. In the standard picture, dark matter is cold, meaning its particles moved slowly enough in the early universe to clump on small scales. Those clumps became halos. Gas collected inside them. The first halos were small, and larger halos formed by mergers. This broad framework works remarkably well for the cosmic microwave background and the large-scale distribution of galaxies. But Webb's early galaxies put pressure on the timeline of what happened inside some of those halos. If luminous galaxies appeared quickly, then either the halos were rare but efficient, or the gas conversion process was stronger than assumed, or our census of halos and galaxies at early times still contains biases. The strongest defense of standard cosmology is that it has not failed where it is most secure. The cosmic microwave background still gives an extraordinarily successful description of the early universe's composition and geometry. Large-scale clustering still supports the dark matter and dark energy framework. Gravitational lensing still points to invisible mass. Webb's surprises occur mainly in the messy baryonic world, where gas cools, stars explode, dust forms, black holes feed, and feedback loops become hard to simulate. A model can be correct in its broad cosmological skeleton and incomplete in the biological, smoky, turbulent details of galaxy growth. That defense is powerful. It is also not the end of the story. The early objects Webb sees are not merely small corrections. Some involve black holes, dust, ionized gas, and star formation at times when the universe had barely begun to produce heavy elements. If the answer is only better feedback modeling, that is still a major change. It would mean the first galaxies were not weak candle flames slowly taking hold. They were furnaces running at high efficiency in dense cosmic neighborhoods. The presence of dust at very early times is especially revealing. Dust is not primordial. The Big Bang made mostly hydrogen and helium, with tiny traces of light elements. Carbon, oxygen, silicon, iron, and the ingredients of dust are made by stars and dispersed when stars die. If Webb detects dust or oxygen in a very early galaxy, that galaxy has already hosted stars massive enough to create heavy elements and release them into the surrounding gas. The clock is not measuring just the age of a galaxy. It is measuring the time required for at least one cycle of stellar birth, death, enrichment, and rebirth. Massive stars can move quickly through that cycle. Unlike the Sun, which lives for billions of years, very massive stars can burn through their fuel in a few million years. That means chemical enrichment can begin early, but there is still a sequence that must occur. Gas must collapse. Stars must form. Massive stars must die. The debris must mix into surrounding gas. New stars must form from that enriched material. Compressing this sequence into the first few 100 million years is possible in principle, but it demands efficient conditions. Webb is showing us that those conditions may have been more common than expected. This is not a small philosophical distinction. A young universe that forms stars slowly is one kind of universe. A young universe that rapidly manufactures galaxies, black holes, dust, and ionized bubbles is another. It is still our universe, still governed by gravity, gas physics, radiation, and nuclear fusion. But its childhood becomes more violent and more productive than the calmer story we inherited. The epoch of Ryanization makes the point sharper. After recombination, neutral hydrogen filled space. Ultraviolet light from the first stars and galaxies had to ionize that hydrogen, stripping electrons from atoms and clearing the fog. Ryanization was not a single switch flipped across the cosmos. It was patchy. Bubbles formed around luminous sources, grew, overlapped, and eventually filled intergalactic space. Webb is beginning to see galaxies in the middle of that process, including cases where hydrogen emission appears unexpectedly visible very early. JADES-GS-Z 13-1, observed about 330 million years after the Big Bang, showed bright Lyman alpha emission that surprised researchers because neutral hydrogen should have scattered that light heavily at such an early stage. One possible explanation is that the galaxy sat inside an ionized bubble cleared by itself or by neighboring sources. Another is that galaxies or black holes in dense regions created transparent channels earlier than expected. Again, the pattern repeats. Webb does not say the universe is impossible. It says the young universe was uneven, dynamic, and perhaps already organized into environments where some regions evolved much faster than others. That unevenness may be the key to much of the mystery. When people imagine the early universe, they often imagine a single age, as if every part of space matured at the same pace. But cosmic history is regional. Dense environments evolve faster. A galaxy forming at the intersection of filaments can receive gas more efficiently than an isolated system. A cluster progenitor can collect matter rapidly. Nearby sources can ionize gas and change what escapes. A telescope looking deep does not see an average patch of cosmic childhood. It may sometimes catch the rare nurseries where growth accelerated. This is a good counter-argument to alarm. If Webb is finding the brightest and easiest to detect early galaxies, it is naturally biased toward exceptional objects. A telescope does not first reveal the average candle. It reveals the lighthouse. Deep surveys are narrow. Gravitational lensing can magnify unusual systems. Selection effects matter. Some galaxies may look dominant because they are the only ones bright enough to be seen at first. But the reply is equally important. Selection effects can explain why the first detections are bright. They cannot automatically explain why bright detections are numerous, why some are spectroscopically confirmed, why black holes appear so early, or why reionization signatures are already complex. Bias is part of the answer, not a magic eraser. The proper controversy is not between panic and dismissal. It is between two careful positions. Either Webb is mostly revealing expected rare extremes with improved instruments, or it is revealing that the extremes are common enough to force a revision of early galaxy physics. The black holes may be the most unsettling part of that revision. Supermassive black holes exist at the centers of large galaxies today, including the Milky Way. They can reach millions or billions of solar masses. The puzzle is how they became massive so early. If a black hole begins as the remnant of a massive star, perhaps tens of solar masses, it needs time to grow. Gas falling in produces radiation, and that radiation pushes back against further inflow. This sets a natural growth limit called the Eddington limit. A black hole can exceed it under some conditions, but doing so for long periods is difficult. Yet quasars and compact active objects are found when the universe was less than 1 billion years old. Some early black holes appear massive enough that simple growth from small stellar seeds strains the time available. Webb has deepened that problem by identifying small red sources where the black hole may dominate the mass and light of the system. In one lensed object, Abel 2744-QS01, observations suggest a black hole of tens of millions of solar masses in a very compact, chemically primitive environment only about 700 million years after the Big Bang. There are several possible answers, each with consequences. One is heavy seeds. Instead of starting from ordinary stellar remnants, Some black holes may have formed by the direct collapse of massive gas clouds, beginning life with thousands or tens of thousands of solar masses. Another is rapid growth. Early gas-rich environments may have allowed black holes to feed at or above the Eddington rate for significant periods. A third is mergers. Black holes in dense young environments may have combined. A more exotic possibility is that some black holes formed very early from primordial density fluctuations. None of these explanations is yet simple, and none should be sold as settled. The important point is that black holes can distort how we read early galaxies. They can make a small host look brighter. They can contribute broad emission lines. They can heat dust. They can change colors and spectra in ways that mimic old stellar populations. So black holes are both a solution and a problem. They reduce the need for impossibly massive early galaxies, but they introduce a new question. How did such important black holes appear so quickly? This is why Webb's early universe discoveries feel like squeezing one side of a balloon. Push down the galaxy mass crisis, and the black hole growth crisis bulges upward. Push down the black hole explanation, and star formation efficiency rises again. Push down the photometric uncertainty, and spectroscopic conformations keep some of the most interesting cases alive. The universe is not giving us one clean anomaly. It is giving us a network of tensions. The same is true for the cosmic web. Webb did not discover dark matter, and it did not single-handedly reveal the entire skeleton of the universe. That would be another overstatement. But its deep infrared surveys and weak lensing maps add sharper detail to how dark matter and galaxies trace each other over cosmic time. Dark matter bends light, and by measuring subtle distortions in the shapes of many background galaxies, astronomers can infer where invisible mass lies. Webb's sensitivity allows more distant and numerous background galaxies to be included in these maps, improving the view. A 2026 dark matter map using Webb data in the Cosmos field showed hundreds of thousands of galaxies and a blue overlay representing dark matter inferred from weak gravitational lensing. This kind of work matters because galaxies are not randomly sprinkled through space. They form along filaments and nodes in a cosmic web shaped by dark matter. Gas flows into halos through these filaments. Clusters form at intersections. Voids open where matter is sparse. The visible universe hangs on an invisible architecture. This architecture helps explain why the early universe could have uneven growth. In dense nodes, gas can accumulate quickly. In filaments, streams can feed young galaxies. In overdense regions, reionization may proceed earlier. A galaxy at a cosmic crossroads can grow differently from a galaxy in a quieter region. If Webb is looking at objects that formed in rare, dense peaks, those objects are not representative of everywhere, but they are representative of what the universe can do under its most favorable conditions. Here again, the debate becomes subtle. The Standard Model already predicts rare high-density peaks. It already predicts cosmic variance, where different patches of sky contain different numbers of early objects. It already predicts that galaxies form in dark matter halos. So not every surprising early galaxy is a challenge to the model. The real question is quantitative. Are there too many? Are they too bright? Are the inferred masses and star formation rates too high after all corrections? Do simulations reproduce the observations when they include the right feedback, dust, black holes, and selection effects? Or do the observations require a deeper shift? Science lives in that quantitative space. The universe has surprised us before, and it may do so again. It should not say every equation failed. Equations fail only when their predictions are tested and found beyond repair. Right now, the more precise truth is that Webb has exposed a gap between simple expectations and measured early complexity. The gap may close with better astrophysics. It may widen with more observations. That uncertainty is the story. The source of the public confusion is understandable. The phrase earliest galaxy sounds like a single contest with a winner, but the record keeps changing because discovery is a process. First, images suggest candidates. Then spectroscopy confirms some and rejects or revises others. Then mass estimates improve. Then models update. A galaxy that once looked like it might break cosmology may become less massive once active black hole light is subtracted. Another object may become more interesting when oxygen emission is detected at a redshift where few expected it. The frontier moves. This moving frontier does not weaken Webb's achievement. It is the achievement. Webb is not delivering a final answer from the edge of time. It is turning the early universe from an abstract era into an observed population. Before Webb, cosmic dawn was partly a theoretical landscape, drawn from simulations and limited glimpses. Webb is filling that landscape with actual objects, each with spectra, sizes, colors, emission lines, and environments. The question is no longer whether galaxies existed at those times. The question is what kinds of galaxies they were, how common they were, and how quickly they built stars and black holes. There is another reason the story must be handled carefully. The claim that the universe may be older than 13.8 billion years has become popular in some corners because it sounds like a clean fix. If early galaxies look too mature, give the universe more time. But the age of the universe is not a loose number that can be stretched casually. It is constrained by multiple lines of evidence, especially the cosmic microwave background, the expansion history, baryon acoustic oscillations, and stellar ages. Changing the age requires changing a network of measurements, not merely adding a few billion years because it would help a headline. That does not mean cosmology is closed. There are real tensions, including the Hubble tension, where different methods of measuring the expansion rate give different results. There are open questions about dark energy, dark matter, early black hole growth, and the detailed timeline of ionization. But none of this justifies saying Webb proved the universe is older. A more accurate conclusion is this. If early structures continue to exceed model expectations, theorists may need to revisit star formation efficiency, feedback, black hole seeds, dust, the initial conditions of early halos, or even aspects of cosmology. An older universe is one speculative possibility among many, not the conclusion. This distinction is not academic. It is the line between science and mythology. Science can be dramatic without being careless. Webb's findings are powerful enough without pretending they have already overthrown everything. The real drama is better. A successful model survives, but under pressure. A telescope built to confirm and refine the story finds chapters written in a denser, faster language. The question is not whether the universe made galaxies too soon. The question is whether our earlier story underestimated how aggressively the young universe could turn gas into light. To see how aggressive that process could be, imagine a primordial halo fed by cold gas streams. The gas falls inward under gravity. Because the universe is dense, the reservoir is rich. The gas cools through atomic transitions, collapses into clumps, forms massive stars, and those stars inject radiation and explosions back into the environment. In a small, shallow halo, feedback can blow gas out and halt the process. In a deeper halo, the gas may remain trapped, cooling and forming stars again. If inflow continues faster than feedback can expel material, the galaxy becomes a star factory. Now place a black hole in the center, perhaps from direct collapse or from a massive early seed. Gas spirals inward. Radiation from the accretion flow adds light that can mimic stars, heat dust, and change spectra. The black hole can also drive outflows that regulate star formation or compress gas and trigger it. The same object can help explain brightness and complicate the mass estimate. This is the early universe Webb is forcing us to confront. Not a simple nursery, but a turbulent competition among inflow, star formation, feedback, dust, ionization, and black hole growth. This competition leaves traces in spectra. A spectrum is not a pretty picture. It is a confession. It tells us which wavelengths are present and which are missing. Hydrogen lines reveal ionized gas. Oxygen lines reveal enrichment by previous stars. The Lyman break reveals how far light has been redshifted and how much neutral hydrogen it encountered. Broad lines can suggest gas moving rapidly near a black hole. Dust changes colors by absorbing and re-emitting radiation. The shape of the spectrum is the argument written by the object itself. Webb's spectrographs are therefore as important as its images. Images make the public gasp. Spectra make the claims survive. A red dot in an image may be ancient, dusty, or deceptive. A spectrum can establish redshift, reveal chemical content, and separate young stars from active nuclei more clearly. This is why the future of the controversy depends less on the most dramatic images and more on painstaking spectroscopic follow-up. Some of the early Webb tension may also come from how we convert light into mass. A galaxy's mass-to-light ratio depends on its stellar population. Young, massive stars are extremely bright for their mass. Older, low-mass stars are dimmer, but can dominate mass. Dust hides some light and re-emits it in infrared. Star formation histories can be bursty rather than smooth. If a young galaxy forms stars in a violent burst, it can be luminous without being as massive as a calmer model would infer. If it contains a black hole, the distortion grows stronger. This means the phrase massive early galaxy must be used carefully. Massive compared to what? Massive in stars or in total halo mass? Massive as inferred from photometry or confirmed with spectra and dynamics? Massive enough to threaten cosmology or simply massive enough to surprise a particular model? The public often hears a single word. Astronomers hear a chain of assumptions. Webb's job is to break that chain into tested links. The early discoveries have already changed how simulations are being built. Modelers can increase star formation efficiency in early galaxies, adjust feedback strength, include bursty star formation, add contributions from active black holes, and explore different dust properties. Some updated simulations are beginning to reproduce more of the Webb population without abandoning lambda CDM. This is an important counterweight to crisis language. A good model is not one that never needs revision. A good model is one that can absorb new data by identifying which assumptions were too crude. But if the modelers succeed too easily, another danger appears. It becomes tempting to tune everything after the fact. If every surprising observation can be explained by adjusting efficiency, feedback, dust, and black hole contribution, then the theory risks becoming flexible enough to explain anything. That is the stronger counterargument from the skeptical side. The point of prediction is not to rewrite the story after the telescope speaks. The point is to predict what the telescope should find before it looks. Webb has shown that at least some pre-Webb expectations were too conservative. The question is whether revised models make new predictions that can be tested. This is where the next decade matters. Webb will not observe one ancient galaxy and end the debate. It will build samples. It will measure luminosity functions, the number of galaxies at different brightnesses and redshifts. It will identify which objects are powered by stars and which by accreting black holes. It will map how quickly metallicity rises. It will test how ionization progressed in different environments. It will reveal whether the earliest bright galaxies are rare jewels or the visible tip of a much larger population. Only then will the controversy sharpen into a verdict. A strong verdict may still be modest. It may say that lambda CDM remains broadly right, but early baryonic physics was more intense than assumed. It may say that black holes formed from heavy seeds more often than expected. It may say that star formation feedback works differently when gas is dense, metal-poor, and rapidly supplied by filaments. Or it may say that some aspect of dark matter, cosmic expansion, or primordial fluctuation statistics needs revision. The difference between these outcomes is enormous. The first revises galaxy formation. The last revises cosmology. We do not yet know which outcome is coming. That unresolved tension holds the argument together. Webb has not overthrown the universe, but it has made the early universe harder to explain in the old comfortable language. That is enough. In science, a mystery does not need to be exaggerated to be profound. There is a second scale hidden inside Webb's discoveries, and it is not the scale of distance, it is the scale of confidence. Human beings like discoveries to arrive as clean statements. This galaxy is here. This planet has this atmosphere. This black hole has this mass. But the actual work of astronomy is almost never that clean. It is a chain of probabilities. Each link is strong or weak in a different way. A redshift can be secure, while a mass estimate remains uncertain. A spectrum can confirm distance while leaving the power source ambiguous. A galaxy can be real, ancient, and luminous without being as massive as the first headline suggested. This is why Webb has created so much tension in public understanding. The telescope gives images that feel immediate, but the science behind them is layered. First, there is detection, the simple fact that photons arrived and were recorded. Then there is calibration, the removal of instrumental effects, background noise, cosmic rays, detector artifacts, and foreground contamination. Then there is interpretation, where colors become redshifts and spectra become chemical histories. Then comes modeling, where light becomes a star formation rate, a stellar mass, a dust content, or a black hole contribution. The public often hears the final number as if it were directly observed, but much of astronomy is inference disciplined by measurement. That does not make the discoveries fragile, it makes them scientific. A galaxy's distance can be measured more directly when a spectral break or line is identified. A black hole's presence can be strengthened by broad emission, compactness, or gas motion. A stellar population can be constrained by comparing multiple wavelengths, but every claim carries an error bar, and every error bar is part of the truth. The universe does not become less real because our knowledge has margins. It becomes more real because those margins tell us where the next observation must go. One of the most important margins concerns dust. Dust sounds ordinary because it is ordinary in human life, but cosmic dust is a profound marker of history. Dust grains are made of heavier elements. They are born from stars, stellar winds, and explosions. When dust appears in a very early galaxy, it says that the galaxy is not chemically pristine. It says something has already processed primordial gas into richer material. But dust also hides and reddens light. It can make a young object look older. It can conceal star formation. It can make a galaxy's color harder to read. Dust is both evidence of earlier stellar evolution and a veil placed over that evidence. This is why infrared observation matters twice. First, it receives ancient light that has been redshifted by cosmic expansion. Second, it can peer through or detect some of the dust-obscured processes that visible telescopes miss. Webb is not just looking farther. It is looking in a language better suited to the universe's hidden heat, buried stars, and stretched ancient light. Some of the early universe's most important events are not bright blue points in visible space. They are red, dusty, compact, and difficult to classify. There is also a scale of density. The young universe was not merely smaller in age, it was physically denser. Matter occupied a smaller volume. Gas reservoirs were richer. Encounters and mergers could happen in different conditions. Radiation fields were more intense in star-forming regions. The background temperature of the universe was higher. This does not magically make every process fast, but it changes the environment in which galaxies formed. It is not surprising that today's calm galaxies may be imperfect guides to the first star factories. In the modern universe, large spiral galaxies like the Milky Way form stars at a modest pace. Gas clouds collapse, stars ignite, feedback stirs the surrounding medium, and the process continues in regulated cycles. But a young compact galaxy packed with dense gas may operate more like a furnace with all vents open. Star formation can become bursty. The galaxy may convert a large fraction of its gas into stars quickly, then pause or be disrupted by its own feedback. If Webb catches many such bursts, the universe appears unusually luminous at early times. That might not mean every young galaxy was massive. It might mean many were caught in short, violent episodes of high brightness. This burstiness is a powerful explanation because it respects both sides of the debate. It allows early galaxies to appear brighter than smooth models predicted without requiring them to contain impossible numbers of old stars. It also implies that older simulations may have missed the rhythm of early star formation. A galaxy does not need to grow calmly to shine intensely. It can flash, enrich itself, blow gas outward, pull gas back in, and flash again. The early universe may have been less like a city gradually turning on lights, and more like a field of storms. But burstiness creates its own problem. If the bright phase is brief, then finding many bright galaxies at once means either the bright phases were very common, or surveys are biased toward exactly those phases, or both. Again, the answer becomes statistical. Webb must count enough objects across enough fields to determine whether the early luminous population is rare and exaggerated by selection or genuinely abundant. A single dramatic galaxy teaches possibility. A population teaches probability. Cosmology is built on probability. Another margin concerns gravitational lensing. Massive clusters of galaxies can bend and magnify the light of more distant galaxies behind them. This effect is a gift because it lets astronomers see objects that would otherwise be too faint. It is also a complication because magnification must be modeled. Different lens models can produce different estimates of intrinsic brightness and size. A galaxy magnified by a foreground cluster may look more luminous than it truly is until the lensing factor is corrected. When the correction is uncertain, the galaxy's inferred mass and star formation rate are uncertain too. Lensing is therefore both telescope and distortion. It extends Webb's reach, but it also forces the analysis to depend on the mass distribution of the foreground cluster, including dark matter. The more carefully that foreground mass is mapped, the better the background galaxy can be understood. This is one reason Webb's early universe work is tied to dark matter work. To interpret the most distant sources, we often need to understand the invisible mass between us and them. The chain of inference becomes almost poetic in its complexity. A galaxy near cosmic dawn emits ultraviolet light from young stars. The light crosses a foggy universe, still partly filled with neutral hydrogen. Expansion stretches its wavelength into infrared. Along the way, it passes near a massive galaxy cluster whose dark matter bends and magnifies it. Webb records the faint infrared signal. Astronomers correct for the telescope, the foreground, the lens, the dust, the redshift, the stellar population, and possible black hole light. Only then do we speak a sentence such as, "This galaxy existed 300 million years after the Big Bang and formed stars faster than expected." That sentence is simple because the labor behind it is not. And this is why cheap certainty is disrespectful to the discovery. To say Webb proved everything wrong erases the work. To say the surprises are meaningless erases the object. The disciplined position holds both. The inference is complex, and the signal is real enough to matter. There is a third scale, the scale of model hierarchy. When people say a model is wrong, they usually imagine the whole tower collapsing. But scientific models are layered. The expansion of the universe is one layer. The existence of dark matter is another. The growth of dark matter halos is another. Gas cooling is another. Stellar feedback is another. Dust formation is another. The way a black hole changes its host galaxy is another. A failure at one layer does not automatically destroy all the others. A telescope can reveal that galaxy formation recipes were incomplete without invalidating the measured age of the universe. This layered view is essential for science safety. Lambda CDM is not a detailed recipe for every galaxy. It is a cosmological framework describing the universe's main components and large-scale evolution. Inside that framework, galaxy formation requires additional astrophysical modeling. Those models are difficult because they involve processes across enormous ranges of scale, from the motion of gas over hundreds of thousands of light-years down to the birth of stars in dense clouds and the explosions of individual supernovae. Even the best simulations cannot resolve everything directly. They use approximations. Webb is testing those approximations. If the approximations fail, that is not embarrassing. It is expected. What would be embarrassing is pretending they never needed testing. The early universe is precisely where approximations are most vulnerable, because conditions were unlike the nearby galaxies used to calibrate them. Gas was less enriched, densities were higher, radiation backgrounds were different. The earliest stellar populations may have been top-heavy, meaning more massive stars than modern populations. Feedback from those stars may have been intense, but the deep gas reservoirs may have made it difficult for feedback to regulate growth in the same way it does today. The mechanism gives the stronger interpretation its scientific weight. The early universe may have built visible structure rapidly, not because cosmology is fantasy, but because the baryonic physics of the first galaxies was more extreme than our local intuition allowed. That claim is bold enough to matter because it shifts the meaning of Webb's discoveries. It says the problem is not simply that galaxies appeared too early. The problem is that our models may have underestimated the universe's first efficiency. The best opposing view says efficiency can only be pushed so far. Gas must obey cooling physics. Stars must obey lifetimes. Supernovae must inject energy. Black holes must obey accretion limits unless specific conditions allow otherwise. If observations demand too much efficiency across too many objects, then the issue may reach beyond ordinary astrophysical tuning. It may point to heavy black hole seeds, unusual initial conditions, or new aspects of dark matter or early cosmic expansion. This opposing view is not fringe. It is the pressure that keeps the debate alive. The difficulty is that the evidence is still developing. Webb has been operating for only a few years. Early surveys cover finite fields. Spectroscopic follow-up takes time. Some sources are faint enough that interpretation remains difficult. A responsible conclusion cannot be final. But a responsible conclusion can still be forceful. The old slow-growth picture has lost its innocence. The young universe was not as simple as many expected, and any model that treats it as slow, empty, and primitive now has to defend itself against data. There is a consequence for how we teach cosmic history. The classic picture often moves from the Big Bang to the cosmic microwave background to the first stars, to galaxies, as if each stage waits politely for the previous one to finish. Webb encourages a more overlapping story. Dark matter halos begin forming while gas is still simple. The first stars ignite in pockets. Their radiation changes the surrounding hydrogen. Their deaths change the chemical composition. Black holes may form and grow inside the same first systems. Galaxies assemble while reionization is still underway. Dust appears before the universe looks ready for it. The early cosmos is not a staircase. It is a knot. A knot is harder to explain, but it is more truthful. The universe does not separate processes for our convenience. Star formation affects black hole growth. Black hole radiation affects star formation. Dust affects what light escapes. Escaping light affects reionization. Reionization affects gas cooling and future star formation. Dark matter controls where gas goes, but gas can modify the inner structure of halos through feedback. Each process pushes on the others. Webb is showing the knot before it had time to loosen. This is why some of the most valuable Webb observations may not be the record holders. The most distant galaxy gets attention, but the population just behind it may teach more. A record holder says the universe could do something by a certain time. A population tells us how often. A single strange black hole says a pathway exists. Many strange black holes tell us the pathway may be common. A lone early oxygen detection is remarkable. A trend in oxygen abundance across many galaxies becomes a theory of enrichment. Astronomy often moves from marvel to census. First comes the object that surprises everyone. Then come the surveys that make it ordinary or reveal it as rare. The emotional public story loves the first step. The scientific revolution happens in the second. Webb is now moving from marvel toward census. It will keep finding extreme examples, but its deeper legacy may be statistical. The distribution of galaxy sizes, star formation rates, metallicities, black hole activity, and ionized bubbles across the first billion years. The first billion years matter because they set the conditions for everything after. By the time galaxies like the Milky Way began their long growth, the universe had already been seeded with heavy elements, structured by dark matter and carved by ionizing radiation. The later cosmos inherited the consequences of the first luminous sources. If we misunderstand the first billion years, we misunderstand the initial conditions of the visible universe. There is a human tendency to place importance at the end of a story where complexity becomes obvious. We care about planets, life, civilizations, telescopes. But early galaxies are the upstream machinery. They made the elements, radiation backgrounds, and gravitational structures that later worlds inherited. The carbon in biology did not begin with biology. It began with stars. The oxygen in water did not begin with oceans. It began with stellar fusion and explosions. The atoms in a telescope mirror did not begin with engineering. They began in cosmic furnaces whose ancestors Webb is trying to see. This is why the early galaxies are not remote in meaning. Their light is ancient, but their consequences are intimate. They are part of the ancestry of everything made from heavy elements. Even if a particular galaxy Webb observes is not an ancestor of the Milky Way, the processes it reveals are ancestral processes. They tell us how the universe learned to make the ingredients from which later complexity emerged. The more Webb reveals, the less the early universe looks like an empty waiting room. It looks like a dense workshop. Gravity assembled the scaffolds. Gas fell in. Stars ignited. Radiation fought the fog. Explosions manufactured metals. Black holes fed. Dust formed. Small galaxies merged. Some systems flared and faded. Others grew into seeds of later giants. All this happened while the universe was still young enough that, in our old mental picture, little should have been settled. That is the cleanest way to state the wonder, without exaggeration. The early universe was not settled, but it was active. It was not mature, but it was productive. It was not impossible, but it was faster than expected. Webb did not find old modern galaxies placed absurdly close to the Big Bang. It found young ancient galaxies whose light forces us to revise what youth can do. This phrase, what youth can do, is perhaps the most accurate emotional center of the subject. We often associate youth with incompleteness. A young universe should be unfinished. But cosmic youth does not mean weakness. A young universe can be dense, hot in background, rich in inflowing gas, and full of first-time processes that no longer happen in the same way. The first billion years may have been less like childhood and more like ignition. That ignition did not happen everywhere at once. Some regions remained dark longer. Some halos never formed many stars. Some galaxies stayed small. Many early sources are still beyond Webb's reach. The telescope shows us the visible peaks, not every valley. This is why humility remains necessary. We are not watching the whole dawn. We are seeing bright windows through it. Still, Those windows are enough to revise the room. They show that the darkness had architecture. They show that light appeared in organized places. They show that chemical history began early. They show that black holes may not have waited for galaxies to become grand. They show that the first billion years deserve the same complexity we once reserved for later cosmic time. When a theory meets that complexity, the goal is not to protect the theory from embarrassment. The goal is to find the missing physics, or the missing modeling, or the missing data. If the answer is simple, it will be found by better surveys. If the answer is deeper, the anomalies will survive and sharpen. Either way, Webb has already done the essential work. It has forced the question into the open. There is also a philosophical trap hidden in the phrase true scale. Webb sharpened our view of the observable universe, but no telescope can reveal the scale of the whole. Webb observes deeper in some wavelengths, sharper in some fields, and more sensitively in some regimes. It does not see the entire universe. It does not see beyond the cosmic microwave background. It does not detect every galaxy. It does not directly see dark matter. It does not find life by looking at one molecule in one atmosphere. What it reveals is not the final scale of existence, but a larger and more detailed fragment of it. That fragment is still astonishing. Webb's deep fields show galaxies packed across the infrared sky. Some are nearby in cosmic terms, some are ancient, some are magnified by gravitational lenses, some are dusty, some are blue with young stars, some are red and compact and strange. The image looks like a crowded city, but it is really a time-layered archive where objects at wildly different distances and ages lie superimposed on the same patch of sky. The crowding itself teaches humility. A blank-looking region of sky is not empty. It is only beyond the sensitivity of your eyes. Increase the mirror size, cool the instruments, observe longer, and galaxies emerge where darkness seemed to be. This has happened again and again in astronomy. The naked eye found thousands of stars. Telescopes found millions. Photographic plates found nebulae. Hubble showed that many nebulae were galaxies. Deep fields revealed thousands of galaxies in tiny patches of sky. Webb pushed further into red-shifted infrared light and found the early universe more populated than expected. Each step did the same thing to human certainty. It made the universe larger, older in visible memory, richer, and less centered on us. It also made our ignorance more precise. Before Webb, one could argue about the first galaxies in broad theoretical strokes. After Webb, the argument must confront actual spectra, actual redshifts, actual candidates, actual conformations, actual contamination. The mystery becomes harder, not because it is vague, but because it is measured. This is why Webb's discoveries are not only about ancient galaxies. They are about the relationship between observation and belief. A model can be elegant. It can fit decades of data. It can be taught in textbooks. But when a new instrument opens a new regime, the model must face reality again. Sometimes it survives almost unchanged. Sometimes it bends. Sometimes a small discrepancy becomes the seed of a revolution. The only way to know is to keep looking. Consider the cosmic microwave background. It is one of the strongest pillars of modern cosmology. It shows tiny temperature fluctuations from the early universe, variations that later grew into galaxies and clusters. The pattern is exquisitely measured. It supports a universe dominated by dark energy and dark matter, with ordinary matter making only a small fraction of the total. It tells us the universe is about 13.8 billion years old under the Standard Model. Any claim that Webb has destroyed this framework must explain why the microwave background remains so well described. That is a high bar. Most Webb surprises do not clear it because they are not directly measuring the background geometry of the universe. They are measuring astrophysical objects within that universe. This is why many astronomers say there is no cosmological crisis, at least not from early galaxy masses alone. They are not dismissing the observations. They are locating the tension in the right place. But the right place is still important. Baryonic astrophysics is not a footnote. It is where ordinary matter becomes the visible universe. Dark matter can provide the skeleton, but gas must cool, fragment, collapse, ignite, explode, enrich, and recycle. Black holes must form and feed. Dust must be produced and destroyed. Radiation must escape or be trapped. Ionization must complete. If Webb forces a rewrite of this visible story, it changes our understanding of cosmic origins, even if the background cosmology remains. The early universe was also not clean in the way diagrams suggest. We draw timelines with neat bands: recombination, dark ages, first stars, first galaxies, reionization. But nature does not respect our labels. In one region, the first stars may have ignited early. In another, darkness lasted longer. Some galaxies may have formed in dense peaks and raced ahead. Others remained small and faint. Ionization advanced bubble by bubble. Chemical enrichment began locally, then spread unevenly. Cosmic dawn was not a sunrise across a flat horizon. It was a storm of scattered fires. Webb is seeing those fires. Some are brighter than expected. Some may be black holes wearing the disguise of galaxies. Some may be compact starbursts. Some may be gravitationally lensed. Some will be revised. Some will become landmarks. The challenge is to sort them without losing the wonder. A useful way to frame the evidence is as a chain. First, Webb detects an object with unusual colors. Second, photometry suggests high redshift. Third, spectroscopy confirms the distance or revises it. Fourth, models estimate stellar mass, star formation rate, dust, and possible black hole contribution. Fifth, the object is placed into a statistical sample. Sixth, simulations are tested against the sample. At no stage should one link be treated as the whole chain. A headline often jumps from step 1 to step 6. Science cannot. That chain preserves the wonder without sacrificing scientific honesty. It can say the light began its journey when the universe was less than 300 million years old. It can say the galaxy is surprisingly luminous and extended. It can say oxygen or dust at that time implies earlier star formation. It can say some early galaxies appeared too massive until black hole light was considered. It can say the remaining population still challenges models of star formation efficiency. It cannot say physics is over. It cannot say the Big Bang is false. It cannot say Webb proved the universe is older. Those lines are not stronger. They are weaker because they are easier to break. The harder line is better. The early universe did not behave like the simplified version of our theory. It formed light fast. It formed black holes early. It may have built dust and heavy elements sooner than expected. It reionized patchily, perhaps with small galaxies doing more work than once assumed. It hid active nuclei inside compact red sources. It made the first chapter of cosmic history less empty, less slow, and less primitive than the old picture suggested. This revised picture also changes how we imagine the origin of planets. Rocky planets require heavy elements. Heavy elements require stars. If chemical enrichment began early and efficiently in some regions, then the raw materials for planets may have appeared earlier than older conservative timelines implied. That does not mean Earth-like planets formed immediately, and it certainly does not mean life was common at cosmic dawn. But it does mean the pathway from first stars to complex chemistry may have opened sooner in some places. Webb also studies exoplanets, and this part of its mission creates a different kind of public temptation. When Webb detects molecules in the atmosphere of a planet such as K2-18b, the headlines rush toward life. Methane, carbon dioxide, and possible sulfur-bearing molecules can sound like clues from biology. But a biosignature is not a biography. A molecule associated with life on Earth is not automatically proof of life elsewhere. Atmospheric retrieval is difficult. Signals can be weak. Instrument systematics can mimic features. Abiotic chemistry may produce surprises. The same telescope that disciplines cosmology must discipline astrobiology. K2-18b is fascinating precisely because it is ambiguous. It is larger than Earth, smaller than Neptune, and orbits in the habitable zone of its star. Webb observations have supported the presence of carbon-bearing molecules, and some studies have explored possible dimethyl sulfide or related compounds. Other analyses urge strong caution, arguing the evidence is not yet robust enough and that systematics or alternative molecules could explain the data. The scientific lesson is the same as with early galaxies. Webb gives us better evidence, not permission to skip uncertainty. This connection may seem distant from the early galaxy problem, but it belongs in the same account because it reveals the central theme. Webb is not only showing new things, it is exposing how easily we overinterpret faint light. A galaxy's brightness can be mistaken for mass. A red color can be mistaken for age. A spectral feature can be mistaken for a molecule. A possible molecule can be mistaken for life. A surprising population can be mistaken for the collapse of cosmology. The telescope is powerful, but interpretation remains human. That may be Webb's most important controversy. Not whether the universe has been shattered, but whether our confidence has. For generations, astronomy has advanced by replacing the obvious with the measured. Earth looked central until planetary motion said otherwise. The Milky Way looked like the whole universe until Cepheid variables showed other galaxies. The universe looked static until galaxy redshifts revealed expansion. The early universe looked simple until microwave anisotropies showed the seeds of structure. Now, cosmic dawn looked slow and sparse until Webb revealed an earlier richness. The pattern is not humiliation for science. It is science working. A good theory invites the telescope to challenge it. A good scientist is not betrayed when nature is stranger than expected. The betrayal would be refusing to look because the model felt too elegant to test. The James Webb Space Telescope is sometimes called the most powerful eye humanity has built. But an eye alone does not understand. An eye collects light. Understanding begins when that light is compared against a model, corrected for bias, tested with spectra, debated, revised, and placed into a larger framework. Webb's images are beautiful. Its true power is that it makes arguments unavoidable. The argument now is about speed. How fast did darkness become structure? How fast did the first stars enrich gas? How fast did black holes grow? How fast did ionization clear the fog? How fast can ordinary matter, under the pressure of gravity and radiation, organize itself into something recognizable? The old answer was slower. Webb's answer appears to be faster. The debate is how much faster, and by what mechanism. If the mechanism is star formation efficiency, then the early universe was better at making stars than our local examples taught us. That would mean today's galaxies are poor guides to cosmic dawn because their environments are too diluted and chemically mature. If the mechanism is black hole contribution, then the first galaxies may have been co-evolving with central engines earlier than expected, with black holes playing a larger role in shaping young systems. If the mechanism is environmental bias, then Webb is catching rare dense regions that grew ahead of the average. If the mechanism is new physics, then the consequences become deeper, but the evidence must become stronger. The strongest counter-argument deserves room to breathe. Here it is. Webb's early galaxies do not yet overthrow the Standard Model. Many initial mass estimates were based on uncertain photometry. Some candidates will be revised downward. Black holes can make galaxies appear brighter and more massive. Early star formation may naturally be more efficient in dense, gas-rich conditions. Simulations are improving and may reproduce the observations without changing the fundamental age, expansion history, or dark matter framework of the universe. Therefore, crisis language may be misleading. Now, the reply. Even if the Standard Model survives, the data still matter because the Standard Model alone does not tell us exactly how galaxies form stars, grow black holes, make dust, and ryonize the universe. Webb is showing that these processes were already advanced at times when many models expected a more primitive population. The surviving theory may not collapse, but the story inside it must change. The early universe may not be impossible, but it is more efficient than we thought. That is a genuine discovery, not a softened headline. The consequence reaches beyond cosmology. If the young universe formed galaxies and black holes quickly, then the path toward complexity began earlier. Heavy elements appeared sooner in some places. Dust formed sooner. The seeds of future planets may have been laid down earlier. Cosmic structure was not waiting politely for billions of years before becoming interesting. The universe became interesting almost as soon as physics allowed it to do so. This is a profound idea because it changes the emotional texture of cosmic history. We often imagine the early universe as a bare prelude, a long, empty beginning before the real story. Webb suggests the prelude was already intense. The first few 100 million years were not a blank page. They were a compressed epoch of collapse, ignition, radiation, enrichment, and rapid assembly. The first chapters may have been shorter, denser, and more dramatic than we imagined. Think of the universe at 300 million years old. To a human mind, 300 million years sounds immense. Dinosaurs did not yet exist 300 million years before today. Continents were different. Life was ancient already. But to the cosmos, 300 million years after the Big Bang is infancy. It is about 2% of the current age. For a galaxy to be bright, extended, and chemically active at that time means that cosmic infancy was not helpless. Gravity had already gathered gas. Stars had already turned on. Some stars had already died. The universe was already doing irreversible work. The word irreversible matters. Once the first stars made heavy elements, the universe could never return to its primordial simplicity. Every supernova changed the chemistry of space. Every black hole that formed changed the gravitational and radiative environment around it. Every ionized bubble altered what light could escape. The early universe was not merely growing bigger, it was changing character. Webb sees these character changes because infrared light carries the evidence. A distant galaxy's spectrum can show oxygen where none existed at the beginning. It can show dust reddening light. It can show hydrogen emission escaping through ionized regions. It can show compactness, suggesting dense early formation. It can reveal an active nucleus whose black hole grew before its host looked mature. These are not just faraway lights. They are forensic evidence of cosmic transformation. The forensic nature of Webb's work should change how we speak about it. A telescope image is not a photograph in the casual sense. It is a measurement translated into color, processed from photons collected through filters and instruments. It is both visual and mathematical. The beauty is real, but it is not the proof by itself. The proof lives in calibrated counts, spectra, uncertainties, comparison samples, and models. The image invites wonder. The data demands discipline. This discipline is especially important when discussing galaxy counts. It is often said that the observable universe contains around 2 trillion galaxies, far more than older rough estimates of hundreds of billions. But such numbers depend on extrapolating faint populations below detection limits and on how one defines a galaxy across cosmic time. Dwarf systems merge into larger ones. Ancient clumps may no longer exist as independent galaxies. Surveys see different depths and wavelengths. Webb improves the census, but it does not hand us a final inventory of all cosmic structures. The true number is a scientific estimate, not a fixed cosmic trophy. The same is true for the number of stars and planets. There are likely enormous numbers of both, beyond intuitive grasp. Most stars may host planets. Red dwarfs dominate stellar populations. Small planets are common. But translating this into a precise count across the observable universe is difficult. The proper message is not the exact digit. It is that the scale of ordinary cosmic architecture is vast enough that our categories of rare and common must be used carefully. A planet may be rare in one physical sense and still exist billions of times in a universe this large. Webb also reminds us that seeing farther does not mean seeing everything. Beyond the earliest galaxies lies the Dark Age, where no stars had yet formed. Beyond that lies the cosmic microwave background, the wall of last scattering for electromagnetic light. No optical or infrared telescope can see through the opaque plasma before recombination. To probe earlier epochs directly, scientists may need gravitational waves, neutrinos, or future 21-centimeter observations of neutral hydrogen. Webb reaches closer to cosmic dawn than any previous infrared observatory, but the beginning itself remains partly hidden. That hiddenness is not a failure. It is the structure of knowledge. Every instrument opens one window and reveals another wall beyond it. Hubble opened the deep optical universe. Webb opened the red-shifted infrared universe. Future missions may map dark energy, exoplanet atmospheres, or primordial hydrogen more directly. The edge of knowledge is not a line. It is a moving horizon. The moving horizon also shapes the fate of the universe. Webb studies ancient light, but dark energy changes what future observers will see. As cosmic expansion accelerates, distant galaxies will become increasingly red-shifted and eventually disappear beyond the practical horizon of future observations. A civilization in the far future, living in the merged remnant of the local group, may not be able to see the cosmic web, the distant galaxies, or the evidence that the universe was once filled with visible structure beyond their gravitational island. In that sense, our era is privileged. We live early enough to see the deep past before it fades beyond reach. This privilege gives Webb's work a strange urgency. The ancient photons it collects have traveled for billions of years, but the window in which a civilization can interpret them may not last forever. We are not central in space. We are not central in time. But we occupy a moment when the universe is old enough to contain minds and young enough to show those minds its large-scale history. The telescope itself is a product of that history. Its gold, silicon, carbon, and metal components were forged by cosmic processes. Heavy elements came from stars and explosions before Earth formed. On Earth, those atoms became minerals, machines, electronics, mirrors, launch vehicles, detectors, and a cold observatory stationed far from home. Matter shaped by ancient stars now studies the first galaxies. This is not a metaphor. It is a physical loop in cosmic history. There is a temptation to end such a story by saying the universe has become conscious through us. That line can be beautiful, but it can also become too easy. The safer truth is enough. In at least one place, matter has organized into beings capable of measuring the universe that made them. Those beings can build instruments that test their own assumptions. They can be surprised without surrendering reason. They can revise a model instead of worshiping it. That is a rare kind of power. Webb's deepest lesson may therefore be epistemic rather than cosmic. It teaches us how to know when our stories are too smooth. The early universe was not waiting to fit our diagrams. It did not care whether simulations predicted slow growth. It did not arrange its first galaxies to protect our confidence. It simply evolved according to physics, including physics we understand well, physics we model imperfectly, and perhaps physics we have not yet discovered. The difference between those categories is the frontier. We understand gravity well enough to build the cosmic web in simulations. We understand nuclear fusion well enough to describe stellar lifetimes. We understand redshift well enough to turn spectra into distances. But we do not fully understand how the first star-forming regions regulated themselves, how black hole seeds formed so efficiently, how dust appeared so early in some systems, how ionized bubbles grew around the first galaxies, or how all these processes interacted in the densest places. That frontier is exactly where Webb is looking. Its discoveries are not random surprises. They are targeted pressure tests of the first luminous era. The telescope asks the universe, "When did light begin?" The universe answers, "Earlier and more unevenly than you expected." Webb asks, "How quickly did galaxies grow?" The universe answers, "Quickly enough that your simple models are uneasy." Webb asks, "Were the first black holes passengers in galaxies or engines that helped shape them?" The universe answers, "Perhaps engines, perhaps earlier than you thought." Webb asks, "Are habitable conditions common?" The universe answers, "Maybe." But do not confuse a spectrum with a living world. That last warning is important because wonder needs boundaries. Without boundaries, wonder decays into clickbait. A galaxy is not impossible just because it is surprising. A molecule is not life just because biology produces it here. A dark matter map is not a photograph of invisible particles. A high redshift candidate is not confirmed until the evidence holds. The stronger conclusion is not the one that shouts the largest claim. It is the one that knows exactly where the cliff edge of evidence lies and stands there without pretending the ground continues. So what did Webb really reveal about the scale of the universe? It revealed that scale is not only distance, scale is also time, uncertainty, and complexity. It showed that the first few 100 million years can contain more activity than our intuition allows. It showed that a tiny patch of sky can contain objects from nearly the dawn of light. It showed that galaxies, black holes, and ionized bubbles were already interacting when the universe was young. It showed that the cosmos is not simply large, it is layered, and each layer changes the meaning of the one before it. The observable universe may contain trillions of galaxies, but the number alone is not the deepest truth. The deeper truth is that those galaxies have histories. They are not beads on a string. They are products of dark matter scaffolding, gas flows, star formation, feedback, mergers, black holes, dust, and time. Webb pushes into the earliest visible parts of those histories and finds that the opening chapters were not as empty as we thought. This changes how the night sky feels. A dark region between stars is not blank. It may contain infrared light from galaxies whose visible light has been stretched beyond the human eye. A faint red dot in a Webb image may be a young galaxy, a buried black hole, or a clue to rionization. A patch of sky small enough to cover with a grain of sand held at arm's length can contain thousands of galaxies at different epochs. The universe is not merely bigger than intuition. It is denser with history than intuition, and that brings us back to the word impossible. The universe has a way of making the word smaller. When astronomers first saw some of Webb's early galaxies, the temptation was to call them impossible. Some were not as extreme as they seemed. Some were revised. Some remain genuinely challenging. The word impossible should therefore be used sparingly. Often it means not yet explained. Sometimes it means our assumptions were incomplete. Rarely, very rarely, it means the deepest framework must change. Webb's early galaxies live somewhere between surprise and revolution. They are too important to dismiss and too new to turn into final doctrine. They demand better spectra, larger samples, sharper simulations, more honest mass estimates, and deeper thought about black holes and star formation. They do not give permission to throw away everything. They give permission to doubt the parts of the story that were too neat. That is the central claim of this journey. James Webb did not reveal a broken universe. It revealed a younger universe that was more capable than our models allowed. It did not end cosmology. It made cosmology less comfortable. It did not prove that the Big Bang was wrong. It showed that the dawn after the Big Bang was more crowded, faster, and more chemically interesting than expected. It did not replace science with mystery. It gave science a better mystery. And perhaps that is the only kind of mystery worth trusting. Not a mystery built from vague awe or exaggerated headlines, but one built from redshifts, spectra, emission lines, lensing maps, detector noise, model failures, and corrected assumptions. A mystery that gets harder as the data improve. A mystery that survives not because nobody checks it, but because everyone does. Somewhere in the deep field, a galaxy less than 300 million years after the Big Bang sends us light that says young stars were already shining. Somewhere else, hydrogen emission escapes earlier than expected through a fog that should have been difficult to clear. Somewhere inside a little red dot, a black hole may be feeding before its host galaxy has grown into anything familiar. Somewhere in the infrared background, weak distortions reveal dark matter pulling the visible universe into shape. None of these objects knows it is part of a human debate. It simply shines, bends light, absorbs light, or emits light according to physics. The debate happens here, on a small planet orbiting a middle-aged star, where minds built from ancient atoms argue about photons older than Earth. We receive the light late, but not too late to learn from it. We translate it into spectra and images. We compare it to models, we argue, we revise, we look again. This is what the telescope has given us. Not certainty, something better, a sharper confrontation with reality, a chance to discover that the universe was never obligated to match our expectation of a slow beginning. A chance to learn that cosmic dawn was not a quiet fade-in, but a rapid and uneven ignition. A chance to replace the word impossible with a more scientific phrase, not yet understood, and that phrase is not a retreat. It is an invitation. It means the universe is still larger than the stories we use to contain it. It means the first galaxies still have secrets. It means black holes, dust, stars, and dark matter are still negotiating the opening chapters of cosmic history in ways we are only beginning to read. It means the most powerful telescope humanity has built did exactly what it was supposed to do. It did not confirm every comfortable answer. It made the questions better. The light from those early galaxies traveled for more than 13 billion years before touching Webb's mirror. It crossed expanding space while stars formed, galaxies merged, planets cooled, oceans appeared, life evolved, and human beings learned to ask where everything came from. When it finally arrived, it did not say the universe was simple. It did not say the story was finished. It said the beginning was brighter than we thought. That is enough to unsettle a model. It is enough to change a field. It is enough to remind us that every age of astronomy begins with a better instrument and ends with a humbler mind. The universe has not been shattered. Our easy version of it has. And in the ruins of that easy version, the real universe is beginning to show through.